Welcome to Nomenclature, Chemical Names and Formulas. It's going to be your responsibility to be able to do the different classes of nomenclature, including binary, ternary, stock, Greek, and acid nomenclature. Make sure you look at the other lectures on those particular areas of nomenclature. This is a unit on the language of chemistry. If you can't speak chemistry, then it's going to be very difficult to do chemistry from this point forward. This is where we learn the actual language that the chemistry is based on. Here's a rose, very beautiful rose, and it says, in the play Romeo and Juliet, William Shakespeare wrote, "What's in a name? That which we call a rose by any other name would smell so sweet." A rose is rosa in Spanish, warda in Arabic, and julab in Hindi. To truly understand another culture, you must first learn the language used in that culture. Similarly, to understand chemistry, you must learn its language. Part of learning the language of chemistry involves understanding how to name ionic compounds. For this, you need to know how to name ions. So this is the unit for learning the language of chemistry. So you will be at least bilingual by the end of this unit, hopefully. Quite possibly, you'll be multilingual. Ionic compounds consist of a positive metal ion and a negative non-metal ion combined in a proportion such that their charges add up to a net charge of 0. For example, the ionic compound sodium chloride consists of one sodium ion and one chloride ion. Probably you are already familiar with the name and formula of sodium chloride, which is common table salt. But it is important in learning the language of chemistry to be able to name and write the chemical formulas for all ionic compounds. The first step is to learn about the ions that form ionic compounds, such as group 1 is going to be +1, group 2 is going to be +2, group 17 is going to be -1, etc. Some ions called monatomic ions consist of a single atom with a positive or negative charge resulting from the loss or gain of one or more valence electrons, respectively. Cations. Recall that metallic elements tend to lose valence electrons. Lithium, sodium, and potassium in group 1A lose one electron to form cations. All the group 1A ions have a +1 charge. Lithium, sodium, potassium, rubidium, and cesium are all +1. Magnesium and calcium are group 2A metals. They tend to lose 2 electrons to form cations with a +2 charge. Magnesium and calcium, as do all the other group 2 metals. They tend to lose 2 electrons to form cations with a +2 charge. Magnesium +2, calcium +2, as do all the other group 2A metals. Aluminum is the only common group 3 metal. As you might expect, it tends to lose 3 electrons to form a +3 cation, Al+3. When the metals in groups 1A, 2A, and 3A lose electrons, they form cations with positive charges equal to their group number. Figure 1 shows some of the elements whose ionic charges can be obtained from their positions in the periodic table. Figure 1, the representative elements shown form positive ions with charges equal to their group numbers. Applying concepts. Are the ions anions or cations? So let's look at figure 1 and let's look at their representative elements and see what positive elements, what positive ions they will form. So this is group 1A and 2A. 1A forms +1, 2A forms +2, and 3A forms +3. So these are the alkali metals, the alkali earth metals, and group 13. This is the other number. This is the numbering we use. Although the book uses the American model, we use the international model, the IUPAC model. So this is 1, 2, and 13. The names of the cations of group 1A, group 2A, and group 3A metals are the same as the name of the metal, followed by the word ion or cation. Thus, Na+1 is the sodium ion or cation. Ca+2 is calcium ion. Al+3 is the aluminum ion, anions. Nonmetals tend to gain electrons to form anions, so the charge of the nonmetallic ion is negative. The charge of any ion of a group A nonmetal is determined by subtracting 8 from the group number. So if it's group 7A, it would be -1. So the elements in group 7A form anions with a -1 charge. So the name of the anion is not the same as the element's name. Anion names start with the stem of the element name and end in IDE. For example, two elements in group 7A are fluorine and chlorine. The anions for these nonmetals are fluoride ion and the chloride ion. Anions of nonmetals in group 6A have a -2 charge. Group 6A elements, oxygen and sulfur, form the oxide anion and the sulfide anion, respectively. The three nonmetals in group 5A, nitrogen, phosphorus, and arsenic, can form anions with a -3 charge. 5 minus 8 equals -3. These have the symbols N -3, P -3, and AS -3 are all called respectively nitride, phosphide, and arsenide. Figure 2 shows the group A elements that form anions. Table 1 summarizes the ionic charges of representative elements that can be obtained from the periodic table. The majority of the elements in the two remaining representative groups, 4A and 8A, usually do not form ions. Checkpoint. What is the name of the anion N-3? Well, above it says nitride. Okay, here is the table with the charges of the groups, the alkali metals, alkali earth metals, halogens, etc. So these are important for you to know, and it's fairly easy. I think it'll be very straightforward. Ions of transition metals. The metals of groups 1A and 2A and 3A consistently form cations with the charges +1, +2, and +3 respectively. Many of the transition elements in groups 1A to 1B to 8B form more than one cation with different ionic charges. Some of these are shown in Figure 2. The charges of the cations of many transition metal ions must be determined from the number of electrons lost. For example, the transition metal iron forms two common cations, Fe+2, 2 electrons lost, and Fe+3, 3 electrons lost. Cations of tin and lead, the two metals in group 4A, can also have more than one charge. Table 2 lists symbols for common ions of many of the metals that form more than one ion. Two methods are used to name these ions. The preferred method is called the stock system. In the stock system, a Roman numeral in parentheses is placed after the name of the element to indicate the numerical value of the charge. Table 2 shows that the cation, iron 2, Fe plus 2, is named iron 2 ion. Note that no space is left between the element name and the Roman numeral in parentheses. The name Fe plus 2 is read iron 2 ion. Fe plus 3 ion is read iron 3 ion and is read iron 3 ion. This is the table 2, which has the symbol, the stock name, and the classical name. Notice that, and I'll go over this in a moment, the ion with the lower charge has us and the higher charge has ik. Doctors provide written instructions to pharmacists about medicines they wish to have dispensed to their patients. It is the responsibility of the pharmacist to prepare the medicines and to advise the patient about possible side effects. Pharmacists also make sure that the physicians have not prescribed a medicine or dosage that could harm the patient. A person with some knowledge of chemistry and biology could become a pharmacist's assistant with on-the-job training. As a part-time job, it's a very nice way to earn some cash. Advancement to the position of pharmacist requires a college degree in pharmacy. This degree includes the study of chemistry, biology, mathematics, and statistics. Pharmacists must also learn about the biological effects of drugs and drug interactions. That's called pharmacology. To obtain a license to dispense drugs, pharmacists are required to pass a state test and must work for a specified period of time under the supervision of another pharmacist. You can also get your doctorate in pharmacy if you continue after you get your undergraduate degree in pharmacy. So it could lead to a doctorate in pharmacy eventually. Colorful solutions of the transition metal ions, cobalt 3, chromium 3, iron 3, nickel 1, manganese 2 are shown in figure 3. An older, less useful method for naming these cations uses a root word with different suffixes at the end of the word. The older or classical name of the element is used to form the root name for the element. For example, ferrum is Latin for iron, so fer is the root name for iron. The suffix us is used to name the cation with the lower of the two ionic charges. The suffix ik is used with the higher of the two ionic charges. Using this system, iron plus 2 is the ferrous ion. Iron plus 3 is the ferric ion, as shown in Table 2. Figure 3. The ions of these transition metals produce an array of colors when dissolved in water. From left to right, the ions are cobalt 3, chromium 3, iron 3, nickel 2, and manganese 2. Now, this particular picture is not very clear, but it will still give you the idea of the colors and the ions that are present. So, cobalt 3, chromium 3, iron 3, nickel 2, and manganese 2. These are the particular solution colors that appear with these particular ions in them. This is a little bit clearer. You see, titanium has 1 color, vanadium has 4, etc. So these colors are a little bit clearer, and they can be used in qualitative chemistry. Notice that you can usually identify an element from what may be an unfamiliar classical name by looking for the element symbol in the name. Thus, ferrous, Fe, is iron, cuprous, Cu is copper, and stannous, Sn, is tin. A major disadvantage of using classical names for ions is that they do not tell you the actual charge of the ion. A classical name tells you only that the cation has either the smaller Us or the larger Ik charge of the pair of possible ions for that element. A few transition metals have only one ionic charge. The names of these cations do not have Roman numerals. For instance, zinc is always +2, and that is a transition element. These exceptions include silver with cations that have a +1 charge, Ag +1, as well as cadmium and zinc with cations that have a +2 charge, cadmium +2 and zinc +2. As figure 4 shows, many transition metal compounds are colored and can be used as pigments. Pigments are compounds having intense colors that can be used to color other materials. For example, compounds of chromium are pigments used to make yellow, orange, red, or green paints. Many transition metals form brightly colored compounds that are used in making artists' paint. Some are natural and some are made in a industrial setting. Some are synthetic and some are natural, as I say. Years ago, many years ago, thousands of years ago, hunters used earth-like tones to make certain colors to paint in their caves. Here are some of the more synthetic types, acrylics, that have colors, bright colors, and those colors are a result of the transition elements that they put in them. Various cadmium compounds range in color from yellow to red and maroon. Prussian blue is an important pigment composed of the transition element iron combined with carbon, hydrogen, and nitrogen. Some ions called polyatomic ions are composed of more than one atom. The sulfate anion consists of one sulfur atom and 4 oxygen atoms. These 5 atoms together comprise a single anion with an overall charge of -2 charge. The formula is written SO4 2. Polyatomic ions such as sulfate are tightly bound groups of atoms that behave as a unit and carry a charge. You can see the structures of 4 common polyatomic ions in figure 5. The names and formulas of some common polyatomic ions are shown in table 3, grouped according to their charges. Figure 5. These molecular models show the arrangement of atoms in 4 common polyatomic ions, interpreting diagrams. How does the ammonium ion differ from the other 3? All right, I want you to look at that and tell me if you can see that. Remember, these polyatomic ions act as individual units. You don't break them down unless they're broken down chemically, and they can tell you that in the problem. But otherwise, you leave them alone. Here we have a tetrahedral shape that's similar to ammonium. Methane is also tetrahedral. You have another example of the ammonium, NH4, and then you see the model, NH4, and that's it. You see the connectivity, atoms and electrons, etc. Here is an example of phosphate, PO4 -2 charge, very tight, very tetrahedral, and you see the double bond there. That's going to resonate, even though resonating is kind of an old term. You're going to get a resonating bond there. The double bond is going to resonate throughout the molecule. Here is nitrate, and it's going to be planar, trigonal planar, and you can see the connectivity, the atoms and electrons, and the Lewis structure, and one extra electron for ion charge. You have 24 total electrons, and that is nitrate. Here is sulfite. Sorry, this is sulfate. I only saw 3 oxygens there. That might actually, the lower left, that actually may be sulfite. Otherwise, the others are sulfate. But that one there looks like sulfite. Could actually, yes, it's sulfite because there's only 3 oxygens and it's a -2 charge. Here are some common polyatomic ions. It would be a good idea to memorize these. You don't certainly have to, but there are some very important ones there. Those are, we won't use many more than that, but periodically we will use some of them. The names of most polyatomic ions end in ite or ate. For example, notice the endings of the names of hypochlorite ion, ClO, -1 charge, and the hydrogen carbonate ion, HCO3, -1 charge. Also notice that 3 important ions have different endings. The positively charged ammonium cation ends in IUM, and the cyanide ion and the hydroxide ion, OH, they end in IDE. Use Table 3 as a reference until you have memorized the contents. Sometimes the same 2 or 3 elements combine in different ratios to form different polyatomic ions. You can see examples in Table 3. It'll pop up in a moment. Look for pairs of ions for which there is both an ite and an ate ending. For example, sulfite and sulfate. For example, notice the endings of names such as, here's some things here. You have chlorite, chlorate. You have sulfite, sulfate. You have nitrite, nitrate. You have a variety of things. For example, notice the endings of names of the hypochlorite ion and the hydrogen carbonate ion, HCO3 -1, and the ClO -1, which is actually bleach. That's the operative thing in bleach. Also notice that 3 important ions have different endings. The positively charged ammonium cation, NH4 +1 charge, ends in IUM, and cyanide, CN -1, and the hydroxide ion, OH -1, end in IDE. Use Table 3 as a reference until you have memorized its content. And you will memorize it just by using it. Trust me. Sometimes the same 2 or 3 elements combine in different ratios to form different polyatomic ions. You can see examples in Table 3. Look for pairs of ions for which there is both an ite and an ate ending. For example, sulfite and sulfate. In the list below, examine the charge on each ion in the pair. Note the number of oxygen atoms and the endings on each name. You should be able to discern a pattern in the naming convention. The charge on each polyatomic ion is a given pair. In a given pair is the same. The ite ending indicates 1 less oxygen atom than the ate ending. However, the ending does not tell you the actual number of oxygen atoms in the ion. For example, the nitrite ion has 2 oxygen atoms, and the sulfate ion has 3 oxygen atoms. All anions with names ending in ite or ate contain oxygen. Checkpoint. What is the formula for the hydrogen sulfite polyatomic ion? When the formula for a polyatomic ion begins with H, you can think of the H as representing a hydrogen ion combined with another polyatomic ion. For example, HCO3 -1 is a combination of H plus and CO3 -2 charge. Note that the charge of the new ion is the algebraic sum of the ionic charges. The hydrogen carbonate anion, HCO3 -1 charge, the hydrogen phosphate anion, HPO4 -2 charge, and the dihydrogen phosphate anion, H2PO4 -1 charge, are essentially components of living systems. In contrast, the cyanide ion, Cn -1 charge, is extremely poisonous to living systems because it blocks the cell's means of producing energy. Figure 6 shows some uses for compounds with hydrogen-containing polyatomic ions. Figure 6, hydrogen-containing polyatomic ions are part of many compounds that affect your daily life. A, sodium hydrogen carbonate, which contains the bicarbonate -1 ion, or hydrogen carbonate -1 ion, can relieve an upset stomach. The presence of dissolved hydrogen carbonate -1, hydrogen phosphate -2, and dihydrogen phosphate -1 ions in your blood is critical for your health. Crop dusters spread fertilizers containing hydrogen phosphate and dihydrogen phosphate ions when they spray crops. So there is the Alka-Seltzer, the sodium bicarbonate, and then the blood containing those very valuable anions, and then the crop duster spraying fertilizer, the least of which in fertilizer is not the phosphorus phosphates, the phosphorus phosphates. At festivals throughout the summer, contestants compete for blue ribbons for the best barbecue. Some cooks say the recipe for their barbecue sauce is key to winning, and they may hint at the secret ingredient. The recipe is the formula for the sauce, a complete list of ingredients and their proportions. With the recipe, anyone could produce a sauce, so a cook is likely to keep a prize-winning recipe a closely guarded secret. Chemistry also uses formulas, but without any secrets. Once you know the rules, you can write the formula for any chemical compound. In this section, you will learn how to write the formulas for ionic compounds. Next, after that, we will learn covalent compounds a little bit, mainly ionic compounds. Here's a barbecue, picture of a barbecue. I'm not very hungry, but I certainly would like a little bit of that barbecue. Excellent. Here is a table of electronegativities. It's going to be very important in evaluating chemical formulas, whether or not they're going to be ionic or covalent necessarily. Ionic compounds are very important. The electronegativity table is very important when it comes to ionic compounds. Binary ionic compounds. In the days before the science of chemistry developed, the person who discovered a new compound often named it anything he or she wanted. It was not uncommon for the name to describe some property of the substance or its source. For example, a common name for potassium carbonate, K2CO3, is potash. The name evolved because the compound was obtained by boiling wood ash in iron pots. Baking soda, NaHCO3, is added to batter to make cakes rise. Plaster of Paris, calcium sulfate monohydrate, is the name of the substance used to make face masks like those shown in Figure 7. Figure 7, these masks are made of an ionic compound with the common name gypsum, calcium sulfate dihydrate. Gypsum is also used in wallboard. Here are the masks made of gypsum, and that is magnesium sulfate dihydrate. When plaster of Paris sets, it forms gypsum calcium sulfate dihydrate. Unfortunately, such names do not tell you anything about the chemical composition of a compound or give you any indication about how it is related to other compounds. The French chemistry, Antoine Laurent Lavoisier, 1743 to 1794, determined the composition of many compounds in his experiments to show how chemical compounds form. As more and more compounds were identified, Lavoisier recognized that it was becoming impossible to memorize all the unrelated names of the compounds. Lavoisier was also executed during the French Revolution by guillotine. They thought he was an aristocrat. He worked with other chemists to develop a systematic method for naming chemical compounds. Their work is the basis for naming compounds today. A binary compound is composed of two elements and can be either ionic or molecular. If you know the formula for a binary ionic compound, you can write its name. First, you must verify that the compound is composed of a monoatomic metallic cation and a monoatomic nonmetallic anion. The compound CS2O is composed of a metal cesium and a nonmetal oxygen. So therefore, it's composed of both of those, so it fits the criteria. Both cesium and oxygen are group A elements, so each ion has only one charge. To name any binary ionic compound, place the cation name first, as it is, such as cesium, followed by the anion name. The name CS2O then is cesium oxide. The name of NaBr is sodium bromide, and the name of SRF2 is strontium fluoride. But suppose you want to name the binary compound CuO. Following the rule above, you would name this compound copper oxide. However, the name copper oxide is incomplete. Recall that copper commonly forms two cations, copper plus 1 and copper plus 2. The names of these ions are copper 1 ion and copper 2 ion, respectively. How can you tell which of these cations forms the compound CuO? Working backward will help. The formula indicates that the copper cation and the oxygen anion combine in a ratio of 1 to 1. You know that the oxide anion always has a -2 charge. Therefore, the charge of the copper cation must be +2 in order to balance the -2 charge. The compound CuO must be copper 2 oxide. The formula copper 1 oxide is Cu2O. Table 2 lists the symbols and names of common metal ions that form more than one ion, and these are generally transition elements. There they are, and they're generally transition elements. They are entirely transition elements, but not all transition elements have multiple oxidation states. The charge is actually called an oxidation state. Recall that the charges of monoatomic ions can be determined from the periodic table. Those of polyatomic ions are shown in Table 3. Using these sources, you can write the names of CnF2 and SnS2. Tin, Sn, forms cations with a +2 and a +4 charge. Fluorine is a group 7A element, so the charge of the fluoride ion is -1. In SnF2, the ratio of the cation to the anion is 1 to 2. Therefore, the charge of the tin cation must be +2 to balance the combined -2 charge of two fluoride ions. The name of SnF2 is tin 2 fluoride or stannous fluoride. However, the name SnS2 is not tin 2 sulfide. Sulfur is a group 6A element, so its charge is -2. The charge of the tin cation must be +4 to balance the combined charges of two sulfur anions. Thus, the name SnS2 is tin 4 sulfide or stannic sulfide. Figure 8 shows examples of uses of stannous fluoride and stannic sulfide. What are the charges of the two ions of copper? Copper 1 and copper 2. Figure 8. Tin 2 fluoride and tin 4 sulfide have different compositions and uses. Tin 2 fluoride is added to toothpaste to prevent cavities. Tin 4 sulfide is used in glazes for porcelain fixtures and dishes. Inferring, what are the charges of the tin ions in the two compounds? Here's the tin 2 fluoride. Someone's brushing their teeth. That's A. And B, the sink, the porcelain sink, is tin 4 sulfide, has tin 4 sulfide in it, and it's a component of glazes. Okay, writing formulas for binary ionic compounds. If you know the name of a binary ionic compound, you can write its formula. Write the symbol of the cation and then the anion. Add whatever subscripts are needed to balance the charges. The positive charge of the cation must balance the negative charge of the anion, so the net ionic charge of the formula is 0. The ionic compound potassium chloride is composed of potassium cations, K+1, and chloride anions, Cl-1. So potassium chloride is a binary ionic compound. The charge of each potassium +1 cation is balanced by the charge of each Cl-1 anion. So in potassium chloride, the potassium and chloride ions combine in a 1-to-1 ratio. Thus, the formula for potassium chloride is KCl. The net ionic charge of the formula unit is 0. The binary ionic compound calcium bromide is composed of calcium cation and bromide anions, Br-1. The two ions do not give equal numeric charges. Thus, each calcium ion with its +2 charge must combine with or be balanced by two bromide ions, each with a charge of -1. That means that the ions must combine in a 1-to-2 ratio. So the formula for calcium bromide is CaBr2. The net ionic charge of the formula unit is 0. Figure 9 shows one step in the process of making steel from iron ore. Hematite, a common ore of iron, contains iron 3 oxide. What is the formula for this compound? Recall that a Roman numeral is the name of an ion, shows the charge of the metal ion. Figure 9, in the process for making steel, iron is extracted from hematite, an ore containing iron 3 oxide. What is the formula for iron 3 oxide? That's for you to answer. Here is the making of steel, giant ladle, unbelievable. Looks like, I don't know, concept of hell, I suppose. All this burning, fiery, melted, schmelted iron, terrible. Thus, iron 3 oxide contains iron Fe+3 cations combined with oxide anions, -2, O-2. How can you balance a +3 charge and a minus 2 charge. You must find the least common multiple of the charges, which is 6. Iron's 3 charges taken 2 times equals 6. 3 times 2 equals 6. Oxygen's 2 charges taken 3 times also equals 6. Thus, Fe plus 3 cation, a plus 6 charge, will balance with 3O negative 2 anions, a negative 6 charge. The balance formula then is Fe2O3. Another approach to writing a balanced formula for a compound is to use the crisscross method. In this method, the numerical value of the charge of each ion is crossed over and becomes the subscript for the other ion. Notice that the signs of the charges are dropped. The formula is correct because the overall charge of the formula is 0 and the subscripts are in the lowest whole number ratio. Yes, this is good as long as they are one is odd and one is even. Otherwise, it doesn't work so well. You have to make corrections. If you use the crisscross method to write the formula for some compound, such as calcium sulfide, you will obtain the result of Ca2S2. The 2-to-2 ratio of calcium and sulfide ions is not the lowest whole number ratio. The formula for calcium sulfide would be CaS. Of course, if the magnitudes of the charges of the cation and anion are the same as they are in this case, the ion combines in a 1-to-1 ratio and the charges are balanced. Checkpoint. Explain why the formula CaS is correct. Plus 2 minus 2. The pearl and the oyster shell shown in Figure 10 are both made of calcium carbonate. Calcium carbonate is obviously not a binary compound because it contains more than 2 elements. Remember that the ate or ite ending on the name of the compound indicates that the compound contains a polyatomic ion that includes oxygen. This compound contains one monoatomic or monatomic ion, Ca plus 2, and one polyatomic ion, CO3 negative 2. Figure 10 also shows a typical automobile battery called a lead storage battery. A lead storage battery. Some examples of ionic compounds containing polyatomic ions are shown. A. Oysters produce calcium carbonate to form their shells and sometimes pearls. B. Lead to sulfate is an important component of an automobile battery. And C. Compounds such as ammonium sulfate or ammonium phosphate are common fertilizers. Here's oysters from various places in the world, and there's a tray of oysters being served. Here's a bunch of car batteries, the lead storage cell, a car battery, variety of them. Here is the lead storage battery, some of the components inside the lead storage battery. Here is an analysis of a fertilizer. You can see ammonium, nitrogen in there. You can see nitrogen, phosphate, potash, and you can see a variety of different things. The potash, the potassium oxide, according to this, and so we have a variety of different anions or nonmetals that in some way, shape, or form help make up the components of the fertilizer. You have the phosphate, helps make up the phosphorus. The nitrogen is NO2 and NO3, negative 1 charge. the potassium soluble potash, K2O, and you have other sources here as well. You have ammonium phosphate, you have ammonium nitrate as well. So, and here's the, these numbers. You see numbers on the bags of fertilizer, and the first number is nitrogen, and the next is phosphorus, and the next is potassium, and it tells you essentially what's the ratio of the components that are in those particular fertilizers. The energy producing reaction inside a battery uses ionic compound lead to sulfate, PbSO4, which consists of the monatomic ion Pb plus 2 and the polyatomic ion SO4 negative 2 charge. The fertilizer mixture, also shown in the illustration, could have been produced from such compounds as potassium hydrogen phosphate, K2HPO4, potassium sulfate, K2SO4, or sodium nitrate, NaNO3. Each contains a polyatomic ion. How would you write the formula for an ionic compound with a polyatomic ion? You would you would do what you did for binary ionic compounds. Write the symbol for the cation, followed by the formula for the polyatomic ion, and balance the charges. For example, calcium nitrate is composed of calcium cation, Ca plus 2, and a polyatomic nitrate anion, NO3, negative 1 charge. In calcium nitrate, two nitrate anions, each with a negative 1 charge, are needed to balance the plus 2 charge of each cation, calcium cation. 1 times plus 2 plus 2 times negative 1 equals 0. The charge is balanced and the ions are in the lowest whole number ratio, so the formula is correct. Parentheses are used around the nitrate ion in the formula because more than one nitrate ion is needed. The subscript 2 that follows the parentheses shows that the compound contains 2 nitrate ions. Use parentheses to set off the polyatomic ion in a formula only when the compound contains more than one polyatomic ion. Very important, you use parentheses. The formula for strontium sulfate, SrSO4, has no parentheses because one polyatomic sulfate ion balances the charge of the strontium cation. When are parentheses used in a formula containing a polyatomic ion? When there's more than one polyatomic ion that has to be indicated to balance the charge so that it is 0. Lithium carbonate is a compound composed of lithium cations, Li plus 1, and polyatomic carbonate anions, CO3 negative 2. In lithium carbonate, 2 lithium cations, each with a plus 1 charge, are needed to balance the negative 2 charge of one carbonate anion. Parentheses are not needed to set off the polyatomic carbonate anion. Lithium carbonate can be prescribed for patients who have mood disorders such as manic depressive or bipolar disorders. A person with bipolar disorder experiences distressing mood swings from elation to depression and back again. The exact mechanism is not known, but lithium ions may exert a mood-stabilizing effect on neurotransmission. Neurotransmission is the process by which messages are sent and received between nerve cells, including those in the brain. So, lithium carbonate is used for mental health disorders, and it helps to stabilize things. Naming compounds with polyatomic ions. You have learned to write formulas for compounds containing polyatomic ions when you were given their names. Now, if you were given the formulas for these compounds, could you name them? When naming compounds containing polyatomic ions, follow these guidelines. First, recognize that the compound contains a polyatomic ion. If the ion is unfamiliar, find its name in Table 3. How would you name the compound LiCN? You could easily think that this compound is composed of individual atoms of lithium, carbon, and nitrogen, lithium cyanide. But you know that lithium is a group 1A element, and that this group forms +1 ions. In addition, carbon is a group 4A element that does not form a monatomic ion. From this, you might suspect that the carbon and nitrogen atoms are part of a polyatomic ion that with a -1 charge. Table 3 confirms your conclusion and tells you that the ion's name is cyanide ion. To name the compound containing polyatomic ions, state the cation first and then the anion, just as you did in naming binary ionic compounds. The name LiCN is lithium cyanide. The compound NaClO is used as bleach and a disinfectant for swimming pools, as shown in Figure 11. The metallic cation in this compound is sodium, Na+1, a group 1A element that forms +1 cations. The polyatomic ion must be ClO, -1 charge. This ion is called hypochlorite ion, so the name for NaClO is sodium hypochlorite. Some ionic compounds containing polyatomic ions do not include a metal cation. Instead, the cation may be the polyatomic ammonium ion NH4 +1 charge. What is the name of NH4 C2O4? The ammonium cation has a charge of +1. Ammonium oxalates. The oxalate anion is C2O4. Sodium hypochlorite, NaClO, is often added to the water in swimming pools to prevent bacteria from exceeding safe levels. Here are 2 pools where you're going to use sodium hypochlorite, keeps everything nice and clean. And here is sodium hypochlorite. It's bleach, and here's a woman that was burned by bleach. And bleach can be very dangerous, especially if it's over the percentages listed there. It's quite deadly. It can be deadly stuff, and very dangerous. The anion must have a charge of -2 to balance the combined +2 charge of 2 ammonium ions. Table 3 shows that the name of the anion, C2O4 -2, is oxalate ion, and ammonium oxalate is named ammonium oxalate. I guess I wasn't supposed to read it that way, but okay, I did. Gold was one of the first metals to attract human attention. When gold was discovered in California in the late 1840s, people from all over the world came to find it and make their fortune. Today, gold is still greatly prized and valued, whereas 1 milligram of gold is worth only about 1 cent. 1 kilogram of gold is worth approximately $12,500. In this case, using the correct prefix milli or kilo makes quite a difference. Prefixes are important in chemistry too. In this section, you will learn how prefixes in the name of a binary molecular compound tell you its composition. We'll look at prefixes. Recall that binary ionic compounds are composed of the ions of two elements, a metal and a nonmetal. Binary molecular compounds are also composed of two elements, but both elements are nonmetals and they are not ions. These differences affect the naming of these compounds and their formulas. Binary molecular compounds are composed of molecules, not ions. So ionic charges cannot be used to write formulas or to name them. In addition, when two nonmetallic elements combine, they often do so in more than one way. So we're looking at molecular compounds. For example, the two elements carbon and oxygen combine to form two invisible gaseous compounds, carbon monoxide and carbon dioxide. Carbon monoxide is illustrated in figure 12. How do you name a binary compound formed by the combination of carbon and oxygen? It might seem satisfactory to call it carbon oxide. However, the two carbon oxides, CO2 and CO and CO2, are very different compounds. Sitting in a room with small amounts of the carbon oxide, CO2, in the air would not present any problems. You inhale CO2 as a product of your body chemistry. Thus, it is normally present in the air you breathe. Carbon monoxide is an invisible gaseous compound of carbon and oxygen. It is a toxic product of incomplete burning, such as occurs in automobile engines and faulty furnaces. The automobile engine knows this, and that's why they have catalytic converters to help convert some of that bad CO into CO2, and then it's given off. Here are some horrific traffic jams. This is just a nightmare, and something's got to give, but this just destroys the environment and someone's ability to live a good life in a city with cars like that. Yuck. On the other hand, if the same amount of the other carbon oxide, CO, were in the room, you would die of asphyxiation. The binary compound CO is a poisonous gas that interferes with your blood's ability to carry oxygen to cells. Obviously, a naming system that distinguishes between these two compounds is needed. Prefixes in the masses of gold samples distinguish between large and small samples. Prefixes in the names of binary molecular compounds help distinguish compounds containing different numbers of atoms. Distinguish compounds containing different numbers of atoms. A prefix in the name of a binary molecular compound tells how many atoms of an element are present in each molecule of the compound. Table 4 lists the prefixes used to name binary molecular compounds. According to the table, the prefix mono indicates the presence of one oxygen atom in carbon monoxide. The prefix di indicates the presence of two oxygen atoms in CO2. The two compounds of carbon and oxygen, CO and CO2, are thus named carbon monoxide and carbon dioxide, respectively. Laughing gas is the common name of the gaseous compound dinitrogen monoxide, which is used as an anesthetic. Here is the table. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. When inhaled, N2O tends to make people laugh. Notice that the second element in the name ends with IDE. The names of all binary molecular compounds end in IDE. Also note that the vowel at the end of a prefix often is dropped when the name of the element begins with a vowel. For CO, you would write carbon monoxide, not carbon monoxide. If just one atom of the first element is in the formula, omit the prefix mono for that element. Here are some guidelines for naming binary molecular compound. So, it says the name of all binary molecular compounds end in IDE. That's key. First, confirm that the compound is a binary molecular compound, that is, a compound composed of two nonmetals. The name must identify the elements in the molecule and indicate the number of each atom of each element. Name the elements in the order listed in the formula. Use prefixes to indicate the number of each kind of atom. Omit the prefix mono when the formula contains only one atom of the first element in the name. The suffix of the name of the second element is IDE. Now, apply these guidelines to naming N2O. The formula shows that the compound consists of two nonmetals, so it is a binary molecular compound. Two atoms of nitrogen are combined with one atom of oxygen. Thus, the prefix of nitrogen is di, and the prefix of oxygen is mono. The name of the compound is dinitrogen monoxide. Using the same guidelines, the name SF6 is sulfur hexafluoride. Notice that it is not necessary to use the prefix mono before sulfur. What about the compound Cl2O8? The binary molecular compound consists of two chlorine atoms, prefix di, and 8 oxygen atoms, prefix octa. The name is dichlorine octaoxide. Suppose you now know the name of a molecular compound and want to write the formula. Use the prefixes in the name to tell you the subscript of each element in the formula. Then write the correct symbols for the two elements with the appropriate subscript. A simple example is silicon carbide. Silicon carbide is a hard material like diamond. It is used as an abrasive and for cutting and grinding, as shown in Figure 13. Figure 13, a grinding wheel made of silicon carbide, SiC, can shape even the toughest material. What causes the sparks? What causes the sparks? Okay, so Figure 13 is going to be the grinding wheel for its calcium carbide. You can see that there. And you can also see silicon carbide is used for trauma plates of ballistic vests. So silicon carbide is tough stuff. Here is a picture of pure silicon carbide, and it's fresh, right hot off the press. Silicon carbide, tough stuff. The name silicon carbide has no prefixes, so the subscripts of silicon and carbon must be 1. Thus, the formula for silicon carbide is SiC. The name of another binary molecular compound is dinitrogen tetroxide. The prefix di before nitrogen tells you that the compound contains 2 nitrogen atoms. The prefix tetra tells you that the molecule also contains 4 oxygen atoms. Thus, the formula for dinitrogen tetroxide is N2O4. N2O4. Some ants can give painful stings when threatened or disturbed. Certain ant species called formicines have poisonous glands that produce venom containing formic acid. Formicines protect themselves by spraying this venom on their predators. Formic acid can stun, or even kill the ant's most common enemies. The formicine attack on a human, however, is much less severe. The contact of formic acid with the skin usually results in blistering. In this section, you will learn the names and formulas of some important acids, such as formic acid. What we're going to learn in this section is the nomenclature of acids. Here is the various ants that can spray formic acid, and our friend the soldier ant from the movie Ants with Woody Allen. Here's an ant. A formicine ant kills a soldier termite. They had termites on the movie Ants as well. I think the name of the movie was Ants. I don't remember altogether. That's in South Africa. And then you have acids are a group of ionic compounds with unique properties. As you will see in Chapter 19, acids can be defined in several ways. For now, it is enough to know that the acid is a compound that contains one or more hydrogen atoms and produces hydrogen ions, H+1. When dissolved in water, acids have various uses, one of which is shown in Figure 14. Figure 14, to create designs such as this on glass, the glass is first coated with wax, and the design is drawn through the wax. When the glass is dipped in hydrofluoric acid, HF, the acid etches, eats away the glass wherever the wax had been removed. It's called glass acid etching. And there's some etching. There's some wheat or flowers or something. I don't know what it is. Looks kind of nice, but the hydrofluoric acid is really what's doing it. There's a mug with Batman, all right, and there's another glass there with some kind of weird thing going on there. Okay, now, naming acids. When naming an acid, you can consider the acid to consist of an anion combined with as many hydrogens as are needed to make the molecule electrically neutral. The cation is always hydrogen for an acid, any kind of acid. Therefore, the chemical formulas of acids are, in general, form H and X, where X is the monatomic or polyatomic anion, and N is a subscript indicating the number of hydrogen atoms that are combined with the anion. Now, don't forget that H is always the cation. The anion can be a single element. If it's a single nonmetal, then it's going to be hydro, the root, and then ic, hydrochloric, hydrobromic, hydrofluoric. If the anion is a polyatomic ion, you just use the name of the polyatomic ion with no further consideration of suffix or prefix. 3 rules can help you name an acid with a general formula H and X. Read the rules and the examples carefully. Notice that the naming system depends on the name of the anion. Each of the rules deals with an anion with a different suffix, ide, ite, and ic. When the name of the anion, X, it ends in IDE, the acid name begins with the prefix hydro. The stem of the anion has the suffix ic and followed by the word acid. Therefore, HCl is named hydrochloric acid, and H2S is hydrosulfuric acid. When the anion name ends in ite, the acid name is the stem of the anion with the suffix us, like sulfite becomes sulfurous. You have to add that extra syllable. Followed by the word acid. Thus, H2SO3 becomes sulfurous acid. When the anion name ends in -ate, the acid name is the stem of the anion with the suffix -ic, followed by the word acid. Thus, HNO3, aqueous, X equals nitrate, is named nitric acid. The three rules are summarized in Table 5. Use the table to help you write acid names until you become an expert. For instance, phosphate, phosphoric, add an extra syllable. Phosphite, phosphorus. Nitric is from nitrate. Nitrite, nitrous. Carbonate, carbonic. Chlorate, chloric. Chlorite, chloris. Hypochlorite, hypochloris. Perchlorate, perchloric. So just get used to the suffix on the end. Here is the table, and you have more. You have three nice examples of how it works, and that's the end. So, ide for a binary acid, it's the hydro root, and then ic all the time. I just take exception with one thing they said. They said if it's ide, you put in hydro root ic. I take exception to that. If it's a binary acid, you use the hydro prefix. Not if it's ide, because cyanide is not, that's not going to become a binary acid, it's going to become a ternary acid. So ternary acid nomenclature is what they described. You put the name of the polyatomic ion with ate is ic and ite is us. And cyanide is a polyatomic ion, but it ends in IDE, but you don't put hydrocyanic acid. So the hydro prefix is for binary acids. I take exception to that one thing that they said. If you know the name of the acid, you can write its formula. Use the rules for writing the names of acids in reverse to write the formulas for acids. For example, what is the formula of hydrobromic acid? Following Rule 1, hydrobromic acid, hydro prefix and ic suffix must be a combination of a hydrogen ion and bromide ion. The formula for hydrobromic acid would be HBr as a result of that. How do you write the formula for phosphorus acid? Using Rule 2, hydrogen ion and phosphite ion must be the components of the phosphorus acid. The formula of phosphorus acid is H3PO3. Note, do not confuse phosphorus with phosphorus, the elemental name. Finally, what is the formula for the formic acid, the defensive weapon of ants you read about in Connecting to Your World? So, according to Rule 3, formic acid must be a combination of hydrogen and formate ion, HCOO. The formula for formic acid is HCOOH. Many industrial processes, including steel and fertilizers manufacturing, use acids. In the laboratory, you will regularly use a few common acids, such as those listed in Table 6. You should become familiar with their names and formulas. When does an acid name begin with the prefix hydro? When it's a binary acid. Not IDE, it's when it becomes a binary acid. And then you're all on the same page. When it becomes a binary acid. Okay? So here's some common names: hydrochloric acid, sulfuric acid, nitric acid, acetic acid, phosphoric acid, and carbonic acid. We'll use all of them with the exception of possibly sulfuric acid. Another group of ionic compounds is the bases. A base is an ionic compound that produces hydroxide ion when dissolved in water. Bases are named in the same way as other ionic compounds. The name of the cation is followed by the name of the anion. For example, sodium hydroxide is a base used in making paper, cleaners, and soap, as shown in Figure 15. To write the formula for bases, write the symbol for the metal cation, followed by the name for the hydroxide ion. Figure 15. Sodium hydroxide is an important industrial and consumer product. A. Recycled paper and wood are digested with sodium hydroxide to make pulp in the first step in making paper. B. Cleaners containing sodium hydroxide, lye, cut through heavy grease. C. An important use of sodium hydroxide is in making soap. Inferring, why is the woman in the second photo wearing gloves? Well, she can get burned, severely burned. I think I showed you some pictures before on people getting burned with these harsh chemicals that are used all the time in cleaning and in washing, and in order to make the soap, you take the fatty acids and you add the sodium hydroxide. Here's paper. That's A. Look at the woman cleaning the oven. What are you going to use? Just regular soap? No, you have to use something really very, very harsh. You need to use the sodium hydroxide. So you use the sodium hydroxide to make soap. That's one of its applications. But you're also using it as a cleaning agent and for cutting heavy grease in an oven. But be careful. It can always cause burns. Chemical burns caused by sodium hydroxide solution photographed 44 hours after exposure. It's finally starting to scab over. And it's horrific stuff, really, in the concentrated form. So make sure you wear gloves and the proper equipment to prevent terrible burns like that from chemicals. Balance the ionic charges just as you do for any ionic compound. For example, aluminum hydroxide consists of the aluminum cation, Al plus 3, and the hydroxide anion, OH negative 1. You need 3 hydroxide ions to balance the plus 3 charge of the aluminum cation. Thus, the formula for aluminum hydroxide is AlOH3 outside the parentheses. That concludes nomenclature. I have a lot of practice videos. Make sure you watch those. That's really what I want you to do. And good luck. Your test is coming up. It's the week after your bonding test, so study hardy, and you'll be fine. Okay? Be well and stay safe.